Welcome to the next lecture in the series on condensed matter theory. In this video I want to talk about the electron correlations and show what electron correlations do by the example of the hydrogen molecule, or as you can also call it, an Hubbard Dimer. And let's start by writing down the Hamiltonian that we have for an hydrogen molecule, whereby we will assume that our atoms are fixed at positions A and B within the molecule. So we have a sum over the electrons, electron 1 and 2, and then we will define a 1-particle Hamiltonian and a 2-particle Hamiltonian. And for the 2-particle Hamiltonian we will sum over all pairs, or we sum over I is not equal to j with a prefactor of 1/2. And then we have the 2-particle Hamiltonian, Ri, Rj, depending on 2 coordinates. Our 1-particle Hamiltonian, depending on 1 coordinate, is given by the kinetic energy, h bar squared over 2m, and then the second derivative with respect to coordinates, and the Coulomb interaction between the nuclei that we assume fixed, the 2 protons that we have, and the electron, 4 pi epsilon 0. And our first electron, or our first proton, sits at position A, and the second nuclei sits at position B, Ra minus R and Rb minus R. The Coulomb interaction between our 2 electrons is E squared over 4 pi epsilon 0, and then just the distance between the electrons, or 1 over the distance between the 2 electrons. So just the normal Schrödinger equation for an hydrogen atom. Now, in order to solve this, we will use second quantization. So we define a basis where we can put our electrons in, and then we can write our Hamiltonian as a sum over the basis functions tau and tau prime and spin. And we have some prefactors giving you the 1 electron energies where you hop from a state with quantum number tau to a state with quantum number tau prime, conserving the spin. And then we have the 2 electron interactions where we have 4 basis functions involved. And the Coulomb interaction as a prefactor depending on the basis functions that we have, and then 2 creation operators. Where a state with quantum number tau double prime can hop to a state with quantum number tau prime and conserve its spin, and a state with quantum numbers tau triple prime can hop to a state with quantum number tau. If you want to relate these prefactors to the Hamiltonian that we had before, we can write them as integrals over our basis functions, where we have the basis function tau complex conjugated h1 of r psi tau prime of r integrated over space, and the Coulomb interaction, which depends on 4 basis functions, is given as a double integral over R1 and R2, where we have our state at R1 and our state at R2, then the Coulomb interaction, and then the state at R1 and the state at R2, dr1, dr2. And here we have to look at our indices. Tau prime couples to tau double prime, and tau couples to tau triple prime. Now, within our model, we will take as a basis the 1s orbital either centered at site A or at site B, which means that tau has as a basis function either 1s centered at A or 1s centered at B. Two options, so there are 2, 4, 8, 16 possible integrals for u and 4 possible integrals for epsilon, but by symmetry many of them are related to each other. So we're going to introduce a few parameters that represent the symmetry different integrals. And let's start with the one electron parameters. Epsilon s, which is the on-site energy, and that is the integral of the 1s orbital centered around site A, h1 of our psi 1s centered around A. And of course, if you center it around B, they are equivalent. So I'm only going to write one of all the symmetry equivalent integrals that we have. And then we have our hopping integral, again given by the three-dimensional integral, where we now go from the wave function centered around site A to the wave function centered around B. And of course you can switch around B and A here and still have the same integral. Our Hamiltonian with these definitions for the one particle part becomes a sum over spin, and then we have our integral, and we have the on-site energy either for the electron sitting at site A or sitting at site B, and we have the hopping, and again we can switch around site A and B. You can either hop from site B to A or from site A to B. Now we can do a similar trick for the Coulomb integrals, or we can introduce similar parameters for the Coulomb integrals. But for the Coulomb integral we have to realize that we have many more possibilities. So the Hamiltonian, where we create and annihilate two particles, tau sigma, tau prime sigma prime, tau double sigma prime, tau triple sigma. Now, in order not to have to write down all these integrals, let's do some graphical representations of these integrals, and the process where you can scatter between your orbitals in the general way, we will write down as a Feynman diagram, where the orbital at tau triple prime with spin sigma is going to tau with spin sigma, and the orbital with quantum numbers double prime and sigma prime will go to tau prime and sigma prime. And the integral that you have is exactly written down here. So you can completely calculate for such a diagram what the parameter or the strength of that interaction would be. Now let's have a look at the inequivalent quantum numbers that we can put in here for our Hubbard Dimer or the hydrogen molecule. First of all, we can look at particle number conserving or occupation number conserving. Diagrams. And we can scatter from side A to side A, where another electron scatters from side A to side A. And we have the spin, but the spin will always be sigma prime on top and sigma on the bottom. This integral we will call a half U1. So that is the Coulomb interaction that you have when two electrons sit at the same site. And of course this means that sigma prime must be different from sigma, but if not, then your creation and annihilation operators will put a 0 in front. Then we can also have the case where an electron on side B scatters to an electron on side B because of an electron on side A. So this we will call an half U2, the Coulomb repulsion between the electrons when they sit at different sites. Now there is one more diagram that we can draw that conserves the occupation. And we will start by saying that an electron from side B scatters to side A, and simultaneously an electron on side A with sigma scatters to B. Now I say simultaneously within the Schrödinger equation. It is of course simultaneously. In the Dirac equation it still is, but when you would do, or the Dirac-Coulomb equation it still is. If you do quantum electrodynamics, then you would say, well, an electron comes, it interacts with a photon and goes to a different side. That photon comes and interacts with the other electron. But then you have some dilation in there. But if you integrate it out in your low energy Hamiltonian, this looks like an instantaneous process. This we call an exchange integral, and we will call this the parameter Q2. Now we have also Coulomb integrals that do not conserve the occupation, and we can have a Coulomb integral that changes the occupation by 1. A sigma prime goes to B sigma prime because we have another electron either at side A or at side B. It would give you the same integral, and we will call this Q1. And then we have an integral where two electrons at the same time change side. So that is a pair hopping interaction. And in this case it's a pair hopping from two electrons at side B hopping to two electrons at side A. Now this interaction is a multiplication of the wave function at side B times A at R1, B at A, B times A at R2, and then integrated over R1 and R2. And that is actually the same as what we have here for the exchange integral. So also this is a half Q2. So in the end, the parameters that we have are epsilon S0, SS sigma, U1, U2, Q1 and Q2. And the reason that I put in here as 0 is because, well, we can slightly reorder our parameters, and we'll do that later, such that, for example, here this Coulomb interaction which changes an electron from side A to side B will be absorbed in the definition of SS sigma. And also in the Coulomb interaction we can rearrange these a little bit, such that we get a few large terms and a few small terms that we can neglect. Besides the parameters for the Hamiltonian, we also have to define our basis. And we already talked about the one particle basis states. And for the one particle basis states, we can define a local basis, which is given by either having an electron at side A with spin up, or an electron at side A with spin down, an electron at side B with spin up, or an electron at side B with spin down. So these are the 4 states that we have on a local basis for the single particle states. Now we want to have 2 electrons in our hydrogen molecule, so we also need to define a 2 particle basis, and again using the local 1 particle orbitals we now can look at all possible combinations to put 2 electrons in these states. And for that we can write down the possible combinations that we can make. We can have both electrons on side A, and instead of having to write down all the creation operators, let me just use a shorthand where we say we have A up, A down, we have B up, A down, and now I have to look such to make sure that I have the same order everywhere. We have A up, B down, and I have B up, B down. Then we have the A up, B up, and we have the A down, B down state. Now the order matters, because if you change the state B up, A down to the state A down, B up, that would just be a minus sign in the basis state, so that would introduce minus signs in your Hamiltonian. So the Hamiltonian on this basis is given here, and we see that indeed what we argued before already, the hopping between the 1 electron states will get modified because of the process with Q1. So you see that everywhere where you have a hopping term as a sigma, there is actually a hopping as a sigma 0 plus Q1, such that it would make sense to redefine some of our parameters. You also see that this Hamiltonian, we know that the total Hamiltonian commutes with spin, so Sz should be a conserved quantum number. The first four basis states have an Sz is 0, then we have a basis state with Sz is 1 and a state with Sz is minus 1, and these 2 states don't interact with any other because Sz is a conserved quantum number. Now let's make a few transformations. The one that we already announced to make is that we're going to introduce SS sigma 0 plus Q1. So the hopping due to the kinetic energy and the potential of the nuclei, plus the hopping because we have Coulomb interaction between our electrons. Then I'm going to define U as the difference between the Coulomb interaction when 2 electrons sit at the same site and the Coulomb interaction when 2 electrons sit at different sites. And I'm going to do some of the exchange interaction in there, and then we'll define epsilon s as epsilon s 0 plus a half U2 minus a quarter Q2, and why we exactly pick this will become clear later, and I can now define also the exchange integral Q2, the Hund's rule exchange between the electrons. And with that the Hamiltonian becomes of this form. Now we see that we don't have a dependence on U1 and U2 anymore, but only on U. So U tells you what the energy is when 2 electrons sit at the same site compared to the energy that you have when the electrons sit at different sites. So it's the difference in Coulomb repulsion that you have when the electrons go to the same site. The nice thing is that with this parameter transformation, your Coulomb repulsion, which in principle is long range, will become short range. And when we later go to lattice models, we will make a similar transformation of your variables. Now for a 2-side model this is exact. For a 3-side model you can still do this, but when you have more sides, it's going to be of course an approximation. But then again, Coulomb interaction might be screened such that you should expect a Coulomb repulsion that falls faster off than 1 over r. And therefore this is still a very useful model. And this is actually the model that Hubbard introduced, and that's why we will call it a Hubbard model, and this is a Hubbard Dimer. And for the Hubbard Dimer, it's just following from parameter transformations. Now let's see how we can rewrite this Hamiltonian in second quantization, and then it also will become clear how we introduced J here. And our Hamiltonian is now given by a sum over the spin. Then we have our on-site energy, A dagger, A sigma, plus, and then the case where we change A to B, plus the hopping, SS sigma, A dagger, A sigma, A B sigma, plus, again, the case where we interchange A and B. Then we have the Coulomb interaction, where we look at the double occupation of site A. So we want to have an electron with spin down at site A and an electron with spin up at site B, A. And of course the case where we interchange A and B. Then we have the term that depends on J, and that is given by the spin at site A dot the spin at site B. These are not vectors, but the spin is a vector. So we have a magnetic interaction between our two sides. The spin parallel or anti-parallel will have a different energy, and because we have a minus sign here and J comes from a Coulomb interaction which is positive, we see that we have ferromagnetic interactions. And this is what we call a direct exchange. What you already see here is that purely based on Coulomb interactions, you will end up with magnetic interactions between your atoms. And in this case, this is a ferromagnetic interaction. There are other ways to get antiferromagnetic interactions between our states, and especially what we will see here is that the Coulomb interaction will favor the singlet ground state and not the triplet. U is of the order of electron volts, J is of the order of 10 to 100 milli electron volt. But both are definitely there. Then we have one more term, which you actually find on the off diagonal here, and that is the pair hopping. You can hop with 2 electrons simultaneously, where the electron at site A moves to an electron at site B. Or B hops to A. So you create at B, you annihilate 2 times on site A, or the other way around. Now we want to diagonalize this Hamiltonian, either here given in second quantization or as a matrix. And in order to do so, we, for the mean field approximations, always used to go to momentum space. Now our dimer is, you could say, not periodic, but if you say, well, I can hop here and then I can hop there again, then it is a periodic system. So we still can go to momentum space and diagonalize the Hamiltonian. So let's define the states in momentum space, and we have 2 k points in our finite site system, which is gamma for the bonding state, where we create a particle at A and create a particle at B with the same phase. and we have the X point in our Brillouin zone for a chain of length 2, where we create a particle at A and we create a particle at B with opposite phase. Now again we can define our one particle basis, but now in momentum space, and this is given as the creation at gamma with spin up, the creation at gamma with spin down, X with spin up, or X with spin down. For one particle states, but now in momentum space instead of real space. Well, our basis is given by a vector, or the basis is spanned by a vector, and this vector is related by a unitary transformation between momentum and local space. I have to put in transposers if you want to say that it is a matrix times vector, then this is better be a column instead of a row vector. The unitary transformation that we have that couples momentum and real space is in principle a Fourier transform, and a Fourier transform here at k is 0 and pi, gamma and x, gives you the bonding and anti-bonding state. Now that's for the one particle basis, but again we have 2 electrons, so we're not necessarily interested in the transformation of your single particle states, but we need to have the transformation of the 2 particle states and the 2 particle basis. So for the 2 particle basis we can define it in a similar way as we did for the local basis, but now in k space we have gamma and x, and again using a similar shorthand we have for the sz is 0 states gamma gamma x, or the xx, where I take spin up, spin down, and then we have the sz is +1 and the sz is -1 state. And we can obtain our basis in momentum state again by a unitary transformation from the local basis, and that unitary transformation is given here. So you see that the sz is 1 and the sz is -1 state are unique because, well, spin, our sz component doesn't interact with each other, and the 4 singlets are mixed. With this we can create our Hamiltonian in momentum space by a unitary transformation of the local Hamiltonian. Now if you do this, then you will find that your Hamiltonian does not completely diagonalize. You have this periodicity, so crystal momentum is a conserved quantum number, but not for each electron separately, but only for all electrons together. So your 2 particle Hamiltonian does not diagonalize anymore after making a Fourier transform. And this of course is a huge problem because we used to be able to diagonalize systems with 10 to the 23 electrons in a mean field theory, because, well, if you have a periodic system, you know that crystal momentum is conserved, and you can make small blocks of crystal momentum for each crystal momentum. That doesn't work anymore when we have electron-electron interactions in our system, so we have to solve this 10 to the 23 electron problem simultaneously for all electrons. Now, you also see that on the off-diagonal you have a half u minus a half j, and actually for the Hubbard Dimer, for the hydrogen molecule, you only find 2 by 2 blocks. So we can easily diagonalize this Hamiltonian. We find for the eigenenergies and eigenstates the following 6 states. Now the ground state is a singlet, then the first excited state is a triplet, where we have our SZ is plus and minus 1 state, plus a state with SZ is 0, because well, otherwise S square wouldn't be a good quantum number. And then we have two highly excited singlets again. Now the ground state singlet is given by two determinants, where you either have two electrons at gamma or two electrons at x. If you think for a one electron state, then the state at gamma is even, whereas the state at x is odd under the exchange of A and B. So our system, our Hamiltonian, has inversion symmetry. So for single electrons you would never be allowed to have them interact with each other. But if you put in two electrons, then you have an even times an even state, which is even, or an odd times an odd state, which again is even, such that indeed having two electrons at gamma or having two electrons at x gives you an even wave function, and they can interact with each other. When the Coulomb interaction U, which now is the difference between the Coulomb interaction of having two electrons on one side or the electrons at different sides, is 0, then you will find that the wave function becomes a state where the state at gamma is doubly occupied, which you would expect for a non-interacting system. Your bonding orbitals are doubly occupied. Whereas when the Coulomb interaction U is much larger than the hopping, than SS sigma, we find that both the state at gamma doubly occupied and the states at x doubly occupied get a prefactor or of 50-50. So then you become an even distribution between the two determinants. Now we can have a look how these states evolve as a function of U, and for that we can have a look at the energy level diagram. In an energy level diagram, we plot the energies of the states as a function of U. Or in principle, for an energy level diagram, you plot the energy of the states as a function of an external parameter, and the external parameter we here choose to be a U for fixed SS sigma. I assumed in this case that U is much bigger than J, and we just set J to 0. We find that the singlet state just stays constant as a function of U. There is no dependence on U, and we know that for the singlet state, the SZ is one state, the electrons sit at side A and B, both with spin up, and then the Pauli principle forbids them to hop, so you never have a doubly occupied state in there. So indeed the energy shouldn't depend on the energy that you have for double occupying your state. Then there is one additional high energy singlet that becomes degenerate with the triplet state when U is 0. And then we have for U equals 0 the doubly occupied bonding state and the doubly occupied anti-bonding state below and above this fourfold degenerate state at U equals 0. When we turn on the Coulomb interaction, we see that the middle two states have a linear energy dependence on U, which you get when you have a diagonal element in your Hamiltonian but no off-diagonal elements. There's no mixing with other states. Whereas the doubly occupied state of the bonding and the doubly occupied state of the anti-bonding state interact with each other, they mix. They become non-single Slater determinants, and they are a superposition of doubly occupied at gamma and doubly occupied at x, and the energy dependence as a function of U is not linear. Now I already talked about the ground state being not a single Slater determinant, but of course in order to determine if that state is correlated, we do not require that you can represent it as a state that is not a single Slater determinant, but we require that you cannot represent it as a single Slater determinant state. So it's a necessary but not sufficient condition. So let's see what our natural orbitals are, and then if on the natural orbital basis our state is not single Slater determinant, is not a single Slater determinant, then we know that the state is not single Slater determinant representable and thus correlated. So let's have a look at the one particle density matrix. And I don't have to do much of diagonalization for the one particle density matrix, because if I look in k-space, then I know that my ground state is given by a doubly occupied bonding orbital plus a doubly occupied anti-bonding orbital with prefactors alpha and beta. So if you just look at the one particle basis where we have A up, A down, B up and B down, then the occupation of A up is alpha square of A down. Sorry, this is not A and B, this is gamma. Here in k-space, gamma and x, and beta square and beta square. And there are no off-diagonal elements. I cannot go from gamma up, gamma down to x up, x down by removing one electron and putting one electron back. So we find that the k-space orbitals are the natural orbitals for our case. And we find that on the basis of k-space orbitals, the ground state is not represented by a single Slater determinant, such that we can conclude that our state is not single Slater determinant representable, and we do have a correlated ground state. And we find that in k-space we have the natural orbitals, which is independent of the Coulomb interaction. Now, instead of looking at single Slater determinant representability of your state, we have also defined a few other characteristics of correlated systems. So we can have a look at the charge fluctuations, for example. And for that, let's first have a look at the charge fluctuations on a local basis. So on a local basis, we can calculate, for example, the occupation of site A, which we define as a sum over the spin A dagger A sigma A sigma. And if we look at the expectation value of the occupation on site A, then this is 1. So if you have a hydrogen atom and you very often measure how much electrons you will find at site A, you will see that on average you will find 1 electron on site A. Now when you do this experiment, you not always will find 1 electron. You might find 0, 1 or 2 electrons. So we can also calculate the variance of the occupation to see what our fluctuations are, and the variance is the equation that we have here. And now we can make an expansion either for the case when U is small or U is large, and you will find that the variance of your local occupation and therefore the charge fluctuations go to 0 when U is much larger than Si sigma. So in the case where you have a very large Coulomb repulsion compared to the hopping, the electrons localize on the sides, and you will always find 1 electron on site A and 1 electron on site B, and there are no longer charge fluctuations. What we already found before, that in this case your wave function is still given by 2 Slater determinants, either having the bonding orbital doubly occupied or the anti-bonding orbital doubly occupied. So having no charge fluctuations does not imply that you're not correlated. but being uncorrelated implies that there is a basis, namely the natural orbital basis, in which you have no fluctuations. Now, instead of looking at charge fluctuations on a local basis, we can have a look at charge fluctuations on a basis in momentum space. So the natural basis or the momentum basis, and we can have a look at the occupation at gamma, which is a sum over all spin, A dagger gamma sigma, A gamma sigma. If we now look at the first moment of that distribution, so the expectation value, then you find is given by the equation here. When u is 0, the occupation becomes 2, because all the states with spin up and spin down are both occupied. When u is very large, the occupation becomes 1, because the ground state becomes a linear superposition of having both electrons at gamma or having both electrons at x. We can now also calculate the second reduced moment, or the variance of the occupation at gamma. And that is given by the equation that we have here. And you see that it goes to 0 when u goes to 0, because, well, you're on the natural basis of your system, independent of u. And when u is 0, your system is uncorrelated. And an uncorrelated system cannot have charge fluctuations on the natural basis of that system. So we see that if we only look at charge fluctuations, when u is 0, you do not have charge fluctuations on the natural basis, or in k-space. When u is very large, the electrons localize and you have no charge fluctuations on a local basis. Now, related to occupations and Slater determinants, we can have a look at configurations. The configurations are defined as the different ways we can put the electrons in the different shells or the different atoms that we have. And we can think of either having the 1s orbital at side A with 1 electron and the 1s orbital at side B with 1 electron. Now, another configuration would be the 1s electron at side A with 2 electrons and the 1s electron at side B, the 1s shell at side B with 0 electrons. And then we can have the 1s shell at side A with 0 electrons and the 1s shell at side B with 2 electrons. This gives rise to 3 configurations. If you look for the case where we have no Coulomb interaction, then you will find that your wave function has a projection on the SA1, SB1 configuration of a half, and a quarter of the states correspond, or the quarter of the determinants corresponds to configurations where you have 2 electrons on side A and a quarter where you have 2 electrons on side B. This is just related to a statistical distribution between your side. We look at wave functions with S at 0, and then there are 2 ways you can put them both on side A and side B, either up, down, or down, up. And there is 1 way you can put both electrons on side A or both electrons on side B. So this is just given by the binomial distribution. Now, for the case where the Coulomb interaction is much bigger than the Hawking, we have seen that charge fluctuations are reduced. You will always have either one electron with spin up and the other with spin down, or you have the case where the electron is with spin down and spin up, and the electrons are never on the same side. Now, besides the ground state, we can also have a look at the dynamics of the system. And the dynamics of the system can be characterized by the response functions. And for the response functions, the first response function that we can think of is a one-electron response function, where you see how your system responds when you remove one electron, or how the system responds when you add one electron. Now, in real experiments, the electron number is of course conserved, but you can think of an experiment where you come in with a photon and you make an excitation where the electron goes from an occupied orbital in your hydrogen molecule to an orbital at very high energy that moves out very quickly, such that it doesn't have any interaction with the local states anymore. For the Hilbert space, or the system under consideration, and the Hamiltonian under consideration, that looks as if you just remove an electron. So we can actually use the linear response that we took for the response of a hydrogen atom to an electromagnetic field, but now instead of saying, well, you create an electron in the p orbital and you annihilate it in the s orbital, just say you annihilate that electron. And we created somewhere high energy that state that doesn't interact with our system anymore. So the response functions that we look at are the photoemission and inverse photoemission. Photoelectron spectroscopy. So the inverse photoelectron spectroscopy is an electron coming in and a photon shooting out. The photoelectron spectroscopy is a photon comes in and an electron shoots out. So our response function, and I'm going to use a g instead of a chi for my response functions here. And I'm going to put in an index I-pass to show you that we relate to an observable, and it depends on the frequency and then on the orbitals where we can add or remove our electron. Well, let's say that we can focus our light such that we can address the atoms separately, and maybe you can analyze the spin such that you also address the spin separately, or your orbitals by polarization dependencies. At least in theory we can always do this. So the inverse photoemission creates an electron in orbital tau prime, and then we have our propagators, and we have two of them, omega minus the Hamiltonian plus the ground state energy plus I0 plus, and then a minus sign, and a pulse at negative energy. And the same we can do for the photoelectron spectra, where we exchange the creation and annihilation operator, but have the same propagators in the middle, and again with a minus sign. Now, if you look back in one of the previous videos or chapters in our script, we defined the one-particle Green's function. And what we see here is very similar to the one-particle Green's function, but not equivalent. And the crux sits in these kind of minus signs. These are observables. And let me outline that very thick. So whenever you do an experiment or you want to describe with your theory something that you can observe, it is these kind of functions that we need to calculate. Now, why then did we not define our Green's functions like this? And the reason for that is that we need a framework where we can talk about self-energies and do diagrammatic expansions. So what is the framework that we want? If we look at our Green's function for an interacting system, then we want to be able to define this as the non-interacting Green's function and some form of self-energy. And we put our poles below the real axis. Now the self-energy, as we have seen, for example, when you do a continued fraction, you say, well, part of my system I can excite into, and then you have the propagation within that system, but then this part can decay, and then the coupling to the rest tells you what your operator is to which you couple, and then the rest of the system that you ignored before becomes then the propagator in the rest. And that self-energy then becomes a real constant and a scaling vector, and is given by a propagator again, a Green's function, with maybe some different on-site energies, and it might even have a self-energy again, so the self-energy of the self-energy. Now, in order for this to work, we have to have all poles below the real axis. And that only happens when the imaginary part of your self-energy is smaller than 0 for all frequencies. If we look, however, at the imaginary part of our response functions, then they are smaller than 0 for frequencies larger than 0, but they are larger than 0 for frequencies smaller than 0. So if I would like to put in real response functions here and then say, well, I look at the real response, the one that you would actually measure, and then couple this to the rest, and I would do that for the retarded and the advanced part separately, then you would see that things go wrong. So we have to decouple this and find a different way to define our Green's functions with respect to the true response functions that you measure. Now, we can do this, and the way we can do this is not so difficult. We're going to define GI pass of omega, tau, and tau prime, and G pass of omega, tau, and tau prime as just a part of our full response function. And the part that we will take will remind you of the rotating wave approximation. And we're going to take a similar approach for the photon emission, the electron removal, and the electron addition spectra. Now, it's no longer truly observable, but well, these poles are on the negative frequency axis. We always sit at positive frequency, so this part will always be larger than that part. You've also seen that the rotating wave approximation has severe problems when you, for example, take the limit to infinite. Things are not causable, you don't respect energy conservation, you do have infinite fast responses. But these are not there to represent physical observables. They are here to be allowed to do diagrammatic expansions. And from those, reconstruct your observables. So the poles of the two functions that we have defined are only when the real part of omega is larger than 0 and the imaginary part of omega is smaller than 0. Whereas for our response function, we have poles when omega is smaller. The imaginary part of omega is smaller than 0, but the real part can either be larger or smaller than 0. Now, we can get the true response function from the one that we defined here, when we take the one we defined here, plus the one where we exchange omega to minus omega, and then we have to take the complex conjugate as well. Now we can also define the Green's function as we defined it before. And for the Green's function that we defined before, we have the combination of the one I pass minus G pass at minus omega tau prime complex conjugated. And with this we flipped the sign of the part that sits with poles at negative frequency, such that the imaginary part is always smaller than 0, and we can do our nice series expansions. Is this a problem? Well, when I know my full Green's function, I can look at the poles. The poles are either at positive or at negative frequencies. With that I can reproduce G pass and Gi pass. From those I can reproduce then my full Green's function. So knowing by adding the Green's function as omega and minus omega complex conjugated. So from the Green's functions that we can calculate diagrammatically, we can, by separating the poles, and from the poles you can calculate of course the imaginary part but also the real part by Kramers-Kronig, construct your Green's functions again and construct the full response that you would measure in an experiment. So we still have a framework where we can go to observables and at the same time can use things like self-energies, because everything sits nicely at negative frequencies, or the self-energy, imaginary part of the self-energy is always negative, such that we can use them as a self-energy in our Green's functions. Now let's have a look at the Green's function for the hydrogen dimer, the model that we have. And let's have a look at the local Green's function. So we remove an electron at site A and see how that propagates, and then see if we can put it back on site A. And what you see here at the bottom, when Coulomb interaction is 0, you can either remove an electron with an energy of SS sigma, that is remove an electron from the bonding state, or you can add an electron with an energy SS sigma to the anti-bonding state. Now, when we include Coulomb interaction, you see that first of all the energy that it takes to add or remove an electron becomes larger, and that there are now two ways that you can remove an electron and two ways in which you can add an electron. You can remove the electron either from the bonding or from the anti-bonding orbital, and the energy difference between them is 2 SS sigma. When U becomes very large, you should get equal intensities, but that's only in the limit where U is much bigger than SS sigma. And then furthermore, you see that the energy difference that you have between the bond of adding an electron or removing an electron is going to the Coulomb interaction that we have in our system. So taking out an electron from one Hubbard Dimer and putting it back to another Hubbard Dimer costs you an energy equal to the Coulomb interaction U. Now, besides looking at the single particle Green's functions or response, we can also look at the two particle response functions or the spin susceptibility. And chi of omega is given as your wave function, and let's make a spin excitation where we flip the spin on side A. A dagger, A up, A down. So we start in our ground state, we take an electron at side A with spin down and turn it to spin up. Then we look at our propagator and you undo it and you see if you come back to the ground state. Now if you look at your spin susceptibility, then for the case where U is 0, you find an excitation at 2s sigma. You can take this local operator, an electron from the bonding orbital, and put it in the anti-bonding orbital. Now, the energy that you see here for your two particle excitations corresponds to the energy that you have in your one particle excitations. You take an electron out from the occupied and you put it in the unoccupied, which is a general property of response functions for uncorrelated systems. Now, when we turn on correlations, you see that the energy that it costs to take out an electron from one Hubbard Dimer and put it onto another Hubbard Dimer is getting bigger and bigger, whereas the energy that it costs for your two particle excitations is getting smaller and smaller. You have a gap inside your one particle spectrum, but within the gap you are able to make two particle excitations. So these two particle excitations do not couple to single charge excitations, and as such they form a new kind of quasi-particles that you can make, that you can propagate, and that you can use to communicate information or energy with. They contribute to things like specific heat, but you can also, well, if you have an extended system, make spin waves with which you can communicate information, and you might even try to make electronics that is then based on spin excitations instead of charge excitations. An advantage would be that the resistivity for spin excitations is generally much smaller, such that you would have less energy loss, which is at the moment one of the biggest reasons that you can't make your electronics and chips bigger, which then would be a spintronics kind of system. And it is these kind of new and emerging quasi-particles that make correlated physics so interesting. Now, last but not least, let's have a look at the self-energy of our system. And for that, I want to go back to the one-particle excitation spectrum, or the one-particle Green's function, because it's for this that I want to define the self-energy. In principle, when you have spin excitations and they couple to additional states, you can also define self-energies for your magnons. They have a lifetime and a line width, so they definitely have a non-zero self-energy. But I want to look here at the self-energy of the one-particle Green's function, and I'm going to look at the one-particle Green's function in momentum space. Now, if you look at gamma, then of course you can only annihilate an electron for the case where U is 0. If you look at X, you can only create an electron when U is 0. At finite U, you have two peaks below and two peaks above the chemical potential, and one of them relates to the states at gamma, the one with the lower energy, and one relates to the states at X, which is the one at higher energy. So G at finite U and momentum X or gamma is given by a spectrum with two peaks, one below and one above the chemical potential. We can write this as the bare Green's function without Coulomb interaction plus some self-energy, where the self-energy now gives how your system is modified because of the Coulomb interaction. We know that without Coulomb interaction, the energy is given by the on-site energy, epsilon s, plus minus ss sigma. We have our s orbitals and they interact, making a bonding and an anti-bonding state, and a splitting between them equal to ss sigma. So our Beer-Green's function is given by 1 over omega plus I0 plus minus epsilon k. The self-energy we can now calculate just by solving the Green's function for the Hubbard Dimer, which you can express analytically. It's just a 2x2 matrix, and calculating the Beer-Green's function, inverting the two, and subtracting them. So the self-energy is given by G0 minus 1 minus the full Green's function minus 1. And for our Hubbard Dimer, this is roughly u over 2 square. I assume here that things like j and q1 and q2 are all 0. 1 over omega minus plus 3 ss sigma plus I0 plus. And the minus corresponds to gamma, the plus corresponds to x. So we see that we have a self-energy that scales as u over 2 square, and the poles sit at plus or minus 3 ss sigma. So there is quite some momentum dependence in your self-energy, so actually we should write here sigma k, because it's not a momentum independent self-energy. And with this we are now able to also use things like self-energies that describe how your particles scatter or are influenced by the Coulomb interaction in your system, compared to a system which you would have described on mean field level. So I hope to have shown you a little bit what correlations do to a simple model that we can basically solve analytically, because it's given by 2 electrons in 4 possible orbitals. Everything becomes 2x2 matrices. You have seen that the ground state becomes non-single slit determinant representable. You can express that also in terms of charge fluctuations or in terms of entanglement. The correlation functions, or the one particle Green's function, the one particle response function, gets additional peaks and structures in the spectrum, and actually that's a very important telltale property of correlations. For an uncorrelated system with n particles, you can have n different energies for removing one of those electrons, but never more. Whereas for a correlated system, you can have a number of particles in the number of orbitals available at this energy, different states, such that you have many more possible peaks in your spectrum. It's actually these kind of peaks and additional structures in the literature have very many different names in different cases, that you find them from just describing that you have a hump, a bump, or a shoulder in your spectrum, to things that are related to the physical interpretation, shake up, shake off states, or in many body language, multiplets, charge transfer excitations. But we'll come to that. But they are always related to having Coulomb interaction, having correlations in your system. And then we have seen that we can relate this to self-energy, and that for the Hubbard Dimer, the self-energy actually gets a very simple expression that relates to a response function with a single pole, which has quite a strong momentum dependence in it. We'll later make approximations where we neglect the momentum dependence of the self-energy. That's not necessarily done because it is true, but it's done because it gives you a handle and it's solvable. You have to start somewhere when you go beyond mean field theory. And we know already that, well, the mean field approximation is not done because Coulomb interaction is small, but because it works. So far, thank you very much for your attention. We see each other later. Stay healthy.